at any point in time. I want to make sure everybody has their questions answered at the right time during the talk. So yeah, I'm going to talk about my research in developing new atomic systems with networking, such that entanglement is improving the resolutions of these sensors. I'll first give sort of a brief overview of atomic sensing and atom interferometry. Then I will discuss how spin squeezing is generated in our experiment and how we're going to use that to improve the sensors. Then I'll discuss how we actually generate two spatially distributed atomic clocks. Once I've described all of the experimental setup, then I'll go into the results about our atomic clock network, and then also the results of the gravity sensing. Atomic sensors we actually use every day, or mostly every day now when we use our GPS to get around. And the point of GPS is that you need to make sure you have different satellites around that are orbiting the planet. All of their clocks have to be synchronized, so that way when you send signals to multiple satellites, you can triangulate your location. So factoring in special relativity and general relativity is important, as well as making sure all of these clocks are synchronized together. So there's a variety of different other types of atomic sensors besides atomic clocks. Well, there's also something called let me turn my pointer on here. We have optical atomic clocks, which are atoms. We use atoms that have optical transitions, so we can get a higher precision when we're measuring time. And those are the types of clocks that are pushing the accuracy of time to like 1 part in 10 to the 20. We also, though all of those experiments are done with Bose-Einstein condensates at very cold temperatures, and they require a lot of fine calibration to get them working. On the other side of the technical spectrum, we have magnetic sensors, which are often built with room temperature atomic vapor cells. So these are a lot easier to manage and deploy. And from a design perspective, the trick is making sure they're compact enough to fit in an airplane or a drone or whatever you need to be putting this into to do magnetic sensing. And then finally, there's gravitational sensing, which I'll describe in a little bit more detail on the next slide. But that's what this picture on the right here. This is a picture from Mark Kasevich's group. This is a 10-meter atomic fountain that they have in the basement of the physics building. And it's this enormous height of the vacuum chamber that allows us to get very high precision. So the way an atom interferometer works is actually very similar and analogous to the way a Mach-Zehnder optical interferometer works. So in an optical interferometer, you have a beam splitter, a mirror pulse, and then another beam splitter to bring them back together. And after you mix them back together on the final beam splitter, you measure the optical, like how many photons you get in each of the two output ports. And the difference between those two tells you information about what was in the path of the interferometer. So in the case here, we are instead using a cloud of atoms instead of photons. So in this diagram here, what it's showing is that you have an atomic sensor that starts with a single spin state of atoms, and you launch them up into the vacuum chamber. Once you apply a laser pulse that acts as our beam splitter pulse, what you can actually do is impart a momentum kick and a momentum flip to half of your atomic state. So now your atomic wave packet is taking two separate locations in space, is traveling along two separate locations in space simultaneously. You can then impart a mirror pulse, which flips both the momentum and the spin, such that they come back together, and you apply a final beam splitter pulse to recombine the two paths. And by measuring the number of atoms you have in one of the spin states versus the other spin state will tell you the quantum phase that they pick up along these different paths. and that is directly proportional to the acceleration of gravity that you can see in this equation up here.
Sorry. So in the final step, you interference the two atomic gas. So it's the four gas interacting. So you can accurately describe their behavior through the gas. Okay.
Yes, right. So the final beam splitter pulse, essentially what it's doing is it's turning the phase difference between the two paths into a population difference that we can measure on a camera.
Okay. So in general, how large is the size of the atomic gas? That's important.
Well, in our experiments, we're using tens of thousands to hundreds of thousands of atoms, but you can use millions of atoms if you'd like to.
Okay.
And all of the physical size, they're all on the scale of between tens of micrometers and a millimeter, depending on what stage of the process is it. Because if it's hot enough, as it takes the entire trajectory of the path, it will expand over time.
So in the calculation, do you do simulation to each atom, or you just assume a atomic cloud to do the calculation?
You can assume that most simply you can assume they're all the same, and that works for very simple interferometers. But if you're doing something, actually I could explain later, if the cloud is too hot or you're going for a very long time and there's maybe distortions of the wavefront of the laser beam that's causing these beam splitter and mirror pulses, there can be errors in, different parts of the cloud might be seeing different intensity of laser pulses. You can implement quantum optimal control pulses where you vary the phase or the intensity of the laser beam over the time of the pulse. So you can do special tricks to improve your sensor. But yeah, and all of those things can be done in simulation.
I see. Okay, thank you.
Yeah.
I have a question about the notation. What is 5G here means? Is the phase evolve with?
Yeah, this is, sorry. Yeah, this essentially is the difference in this phi1 and the phi2.
And what's the G? G is gravity or?
Yes,
no,
G is gravity.
Gravity. Okay, so this is the way to measure gravity wave.
Exactly. So the phase difference, yeah, I should explain this equation better. The K effective, that's related to the momentum that a single atom picks up when it absorbs one of the photons from these laser pulses and gets a momentum kick. G is the gravitational acceleration, and T is the time between these pulses.
I see. Thank you.
Yeah. Okay. So now I'll move on to talk about spin squeezing. So normally when, I guess, physicists think about squeezing, we often just think about quadrature squeezing. So for example, if you had a coherent state of light, or maybe you had some qubit that was in some coherent state of various excitations, generally you have an equal quantum distribution in both quadratures. But you can actually squeeze those states to redistribute the Wigner function. And if you do this cleverly enough, either you can put it in a phase squeezed or an amplitude squeezed configuration, and those are going to depend on what type of thing you want to measure. Maybe there's a certain physical process that alters the phase of your quantum state, in which case you want to do phase sensitive squeezing. But spin squeezing is slightly different. So with spin squeezing, we're actually squeezing the population difference between those two states I showed in the previous slide. We can represent the Wigner function on a multi-particle block sphere. So normally when you see a block sphere, it's representing a single qubit. But here it's representing the whole, let's say, 1 million atoms that are in the atomic ensemble. So the radius of this sphere is proportional to half the number of atoms you have. So if you look at the Wigner function, the quantum distribution, we can think about angular resolution as the width of this pulse of the distribution divided by the radius of the sphere. So when a physical process happens, it's going to alter the phase of the Wigner function on the Bloch sphere. So the smaller that distribution is, the more closely we can detect the thing that caused the phase change. So the way we do that is we generate spin squeezing. And so what the spin squeezing does is it reduces the noise in the spin Z quadrature, which is proportional to the atom number difference. And then in the orthogonal quadrature, we actually lose resolution. But this is okay because we only need to measure one quadrature at the end of the day in order to get our final results. So now I want to tell you why we actually care about spin squeezing in the first place. So this acceleration, this phase change due to gravitational acceleration, we can talk about the sort of the parts per million, say, of sensitivity that you have. It's proportional to 1 over the square root of the number of atoms you have. This is the noise of the coherent state, that distribution of the circular Wigner function. And then you have the momentum transfer and the time between the interferometer pulses. So if you want to improve your resolution, you want to decrease delta G, you can either go to a longer time by increasing T, or you could increase the number of momentum kicks between the two atomic states. And both of those things are done in the equivalence principle test from our lab. So again, this is a 10-meter vacuum chamber. So over the whole course of the sensor experiment, the atoms are experiencing over 1 second of total freefall time. Now, this is extremely large experiment and not very practical, especially if you want to put this thing on an airplane or something like that. So if we want to look at more compact designs, then we can look at entangling the atoms. So for the same number of atoms, we'll just have a improved sensitivity when we look at the spin squeeze states. So now I want to tell you the way in which our experiment generates spin squeezing. So we work with between, I would say, 40,000 and 500,000 atoms of rubidium-87 that we cool down to 20 microkelvin. So this is still in the thermal regime for atoms. The Bose-Einstein condensates that people normally operate these with are normally tend to about 100 orders of magnitude cooler in temperature. All of these atoms are distributed among about 1,000 lattice that are generated in between 2 cavity mirrors. Those are these 2 blue mirrors here. And the light that's sent in creates a standing wave in the center of the 2 mirrors, and that creates a trap for the atoms. So in this picture here, the lattice potential, the red one, you can see that at every, I think it's maximum intensity of light, the atoms are localized in those locations. The key to generating very large amounts of squeezing is by using a dual wavelength cavity. So the light that we actually use to measure the population difference between the atoms, we make sure that the wavelength is twice that of the, the frequency is twice that of the lattice potential frequency. The reason is because you can see in the picture that if you have the probe intensity always synced up with the lattice potential, then the maximum intensity of the probe light will always coincide with the locations of the atoms. So in previous experiments, the probe light was not synced up, and so you're just sort of getting an average of half the intensity among all of the different atoms. Here you're getting the maximum intensity for every atom, so there's a uniform coupling, and you have a much cleaner signal. The way this actual measurement works is through a quantum non-demolition measurement. we send in the probe light that is halfway detuned between the two spin up and spin down levels of the atomic system that we're working with. Specifically, what that means is that we send the laser light into the cavity, and what happens is the cavity interaction is proportional to the amount of light you send in, that's A dagger A. It's proportional to the population difference in the atomic states inside the cavity, and then proportional to this delta, which is cavity coupling strength. Which will be determined by a number of factors, including like the shape of the mirrors, how close the mirrors are, how tight the beam waist is, etc. Effectively, what happens is when there's a shift in the population difference in the atomic states, it actually causes a shift in the resonant frequency of the cavity. The result of this is that the reflected light from the cavity experiences a phase shift. And we can pick up that phase shift with a homodyne detection system, which is pictured right here. So part of the light is used as a local oscillator, and then the other part of the light goes to the cavity, reflects directly back into the homodyne detection system, and then we measure the voltage from a balanced photodetector. So the cavity frequency shift is going to be directly proportional to our voltage on our homodyne detection system. And when you actually do this whole experiment, the best result you can get is you can reduce the variance of that angle on the Bloch sphere by about 100 times below the variance of the coherent state noise. So, yes, go ahead.
Thank you. So in this experiment, you prepare the spin squeeze in Z direction. Or
yeah, we actually prepare the states in an even superposition of the two, so that the mean vector is on the equator of the Bloch sphere.
Okay.
Yeah. Are there any other questions about the experiment setup?
So you're going to use this equipment to measure gravity, right?
Yes.
That's like the purpose.
Yes, that is the final slide. That's the grand reveal.
Yeah. So but you want to reduce the measurement error because you want to use this spin squeezing maybe in Z direction to measure this population. The population of this spin going to reflect the phase, right?
Yes, exactly.
And by reducing the spin, this total spin, the error of total spin, then you expect that the measurement of the phase will be reduced. The error of a measurement in phase will be reduced.
Exactly.
Okay. See, thank you.
Sorry, I may kind of a little confused in terms of the Bloch sphere. You are trying to differentiate the two spins which are very localized in their Bloch sphere position. So they are roughly in the same color region there. So the only difference is only in the Z direction. Is that the case?
Yes.
And usually, what's the difference of the spin? What's the limit you want to achieve?
How good do we want the measurement?
I mean, what's the limit you want to achieve the difference?
The limit. Okay, so the what I said here, where the variance is 100 times below the coherent state, that's pretty much the best you can do, because if you want to increase the interaction strength, this Hamiltonian here, you can increase the number of atoms, which starts to become difficult experimentally, or you can increase the strength of the laser light. But as you increase the strength of the laser light, you start to create spontaneous emission in the atoms. So now you start getting these spontaneous spin flips that ruin your measurement. So getting the 100 times reduction is just about as good as you can do with these types of systems.
Okay, I see. Thank you.
Okay. So here's a picture of what's going on in the experiment. I know it's a bit hard to see, so I'll zoom into different sections. So this is the picture of the vacuum chamber. So you can tell it's not made out of steel. It's instead made out of zero-door glass. And the reason is because this has a very low expansion coefficient with temperature. So any temperature fluctuations in the room are going to keep the size of the vacuum chamber relatively constant. And the reason this is important is because you can see in this picture, these are the cavity mirrors, and they're affixed directly to the vacuum chamber. So this is a really compact design, and it's a very robust design with respect to temperature. To measure the atoms, in addition to doing this quantum non-demolition measurement, you can also measure the atoms with fluorescence measurement. And the camera that we used is, you can see in the lower left corner here, we put an objective lens right up against the vacuum chamber wall, such that we can collect as many photons as possible, which allows us to actually also measure squeezing with fluorescence instead of with quantum non-demolition measurement. And I'll show you what those two different measurements sort of actually look like in the lab. So this is an oscilloscope trace. This is the voltage of that balanced photodiode in the homodyne detection system. So when you see this pulse here, that indicates that the measurement had taken place, and because the voltage was positive, it corresponded to more atoms up than down. And if the voltage was negative, you'd have more atoms down than up. And the height of the measurement corresponds to the size of the population difference. The key feature here is that these quantum non-demolition measurements are conditional, meaning if you only looked at the first measurement, it would look as if you were only measuring the coherent state. What you need to do is measure the atoms twice, both with quantum non-demolition measurements. Then you look at the correlation between the two. So you look at measurement number 2 minus measurement number 1. That is what gives you that squeeze state. So for example, so if you're watching this take data over time, you're going to see these two measurements always going in the same direction. Now, because these are quantum non-demolition measurements, you could just keep taking as many Q&D measurements as you want, and as you keep taking more and more, you're going to get the same results. In order to get a different results, what you can do is you can operate your sensor in between the two pulses. So essentially, the first pulse gives you like a baseline for where your sensor is starting. The sensor evolves in time in between because of gravity or magnetic field. And then the second pulse tells you how far the sensor has changed. We also have the fluorescence measurement, which what we do is we simply separate the two states spatially, and then we can do fluorescence imaging and just count how many photons you have in one position versus the other position. Now, the key thing about the fluorescence measurement is that this is destructive. Once you do fluorescence, you're done with the measurement. And normally this is okay, because all you need to do is you only need to take two measurements, the before and after of the sensor. However, the fluorescence measurement actually does not perform as well as the Q&D measurement in terms of the variance reduction that you get on the measurement. And I can show you that on the next slide. So this is a histogram showing there were about 200 samples taken, and the blue shows you what happens if you only look at the measurement from the first probe only. The orange and yellow distributions are the second measurement minus the first measurement. So this graph is just trying to show you that if you only had one probe, you could not have distinguished these two different angles, the yellow and the orange, without the squeezing. And on the right graph here, this is visually showing you how the two QND measurements are correlated to each other versus how the QND measurement is correlated to the fluorescence measurement. So you can see that even though the fluorescence has reduced accuracy, it's still squeezed, right? A coherent state would just look like a uniform distribution of a circle. But the reason why we actually go and use fluorescence imaging in the first place is because the atoms have to experience free fall if we want them to measure gravity. And if they experience free fall, that means they're going to leave the spatial mode of the cavity, and then we can't use the cavity to make a second measurement. So this fluorescence imaging is extremely necessary.
For the fluorescence image, will it introduce another noise effect?
Yes, it does. And the difficult part of the fluorescence imaging is that the noise sources from fluorescence are not the same as the noise sources for the QND measurement. Right. So when you're doing two QND measurements, a lot of those noise sources are common to both, so they cancel. But now you have different things with fluorescence and quantum demolition. You have to do careful calibration to actually get these two calibrated to each other.
Yeah.
Yeah. Okay. Now I'll describe how we actually, once we've prepared these, or once we have squeeze states, how we can actually separate them in space. So on that first slide, I showed you that these laser pulses that do a beam splitter impart momentum to one of the atoms, or to one of the states of the atoms. Specifically, how that works is if you have the two states, the spin down and the spin up state that you're operating with, you can have a 2-photon transition that is detuned from an excited state. And as long as the two laser pulses that you're sending in have a frequency difference equal to the energy level splitting difference of the atomic state, then you can cause a 2-photon transition that moves the state from one to another. Now, the key here is that if you have the laser beams coming at each other instead of going with each other when they see the atoms are basically absorbing a photon from one of the beams and then emitting it into the other beam. So now you have a net momentum transfer from the photons to the atoms, and that's what generates this momentum kick. And in our situation, this was particularly challenging for a few reasons. One is the temperature. So I mentioned how the temperature is actually relatively hot for these types of systems. The reason you want them small is because they have a low velocity distribution. And these counter-propagating laser pulses are going to be sensitive to the velocity. So in order to get around that, you actually have to go to a higher laser intensity, which can be tricky. You also have phase noise from the laser system due to all of the different modulator elements that you have that are generating the laser frequencies. We also had a compact design, so it was hard to actually get additional laser beams into the system. And then if you're working with a system that magnetic fields can cause changes in the atomic sensor, any biased magnetic fields in the laboratory are going to cause a problem. And in high precision experiments, often you'll want to magnetically shield your sensor, but that's not something that we were able to do in our experiment. So if you can think about the Doppler broadening in terms of frequency, and this frequency corresponds to how quickly you have to actually drive the 2-photon transition. So in order to drive the 2-photon transition quickly enough, we had to go to a much higher laser power than is normally used in these types of experiments. And we also had to use a much smaller detuning from the excited state than we normally do in these experiments. This has caused a number of problems that actually prevented us from going to operate at sensor times as long as we wanted to. but we're confident that in future iterations of an experiment like this, those problems can be addressed more easily. And for those interested, this is just a description of what's going on in the laser system. We start with a narrow line width laser that we impart sidebands on, as you saw in the previous slide. And we use one of the sidebands generated from an EOM combined with a unmodulated beam. And by using the correct amount of optical amplification and optical switching, we're able to very quickly switch on and off the lasers that are being sent to the atoms. So we can just have, on the scale of, I would say 100 nanoseconds, we can switch the light from uncoupled from a fiber to coupled to a fiber and being sent to the atoms. So this helps enable our scheme where we have to operate these pulses very quickly and for very short times. Okay, are there any questions before I move on to the experimental results?
I think I'm good.
Okay. So now let's go from everything I've talked about so far about squeezing has been with a single atomic clock, so to speak. But now we need to think about what happens if you have a network of clocks. If you have two different clocks, for example, and you wanted to measure, let's say, the average angle between them, you would have to measure them each independently. They would each have the noise of the coherent state. And when you added the angles together, their variances would add as well. If we want to improve this result, what we can do is we can introduce correlations between the blue and the red clocks, such that we get a covariance or a correlation or a covariance between them that reduces the total variance of the measurement. So specifically what we do here is if we take two clocks and we measure the sum of both of their spins, now you're measuring the variance of the sum of the two JZ values. But because they are quantum entangled, because there's correlations between the two, you end up getting noise that is below what you would have gotten if you had individual sensors. Specifically, what I'm trying to represent with this picture here, these two spheres, is it's hard because it's depicting really a four-dimensional parameter space, where each of the four dimensions are the spin up and spin down from each spatial location. So what I'm showing here is that, for example, this dark sliver of red here is the distribution that corresponds to you finding a point on the first clock below the equator. So this is sort of a conditional way to explain what the Wigner functions look like. So for example, if you started with if you have a net, if the total spin is 0 and you happen to have measured one below the equator, then that necessarily means the other spin, the clock spin, has to have been above the equator in order for the total sum to be 0.
So I have a question about this part.
Yeah.
How do you prepare the system like that? Because for two atomic system, you need to induce the relation between them. You need to correlate them in some way, right?
Yes.
But now you are talking about two atomic clock. Then how do you do that?
So the way we do that is on the next slide. Good lead in. Thank you. So what we do here is we start with our initial single clock, and then we apply those momentum transfer that we want to use for the gravitational sensor. So now we're utilizing this two photon momentum kick, Instead of using it for the gravitational sensor, we're actually just using it to take the atomic cloud and split it in half. So we give each part of the atomic state, each part of the quantum state gets a momentum kick, and then we wait for tens of microseconds to a millisecond for them to separate in space. Once they've separated in space, we waited a short enough time that they both still remain in the cavity. So at this point in time, we can send in the QND measurement, and that QND measurement now sees both of these two positions in space. But the QND measurement, it doesn't care about where atoms are in space. All it cares about is what the total population difference is. So what the measurement is doing is it's entangling the spins no matter what location they're in. So now we have this entanglement that spans space. Did that answer your question?
Yes, thank you.
Okay, great. So to be even more specific about what exactly we're measuring, I described how it doesn't really matter which direction we squeeze in as long as we're measuring the correct thing. So what we can do is once we squeeze horizontally, we can actually apply a microwave pulse to rotate the states into the vertical direction. And the reason this is important is because for all of the sensors that we use, we're always looking for the phase shifts in between the atomic state and a reference classical oscillator that you have in the lab. So for example, let's say we have, I have like a crystal oscillator that's operating at the same transition frequency as the atomic state. And so now the atoms are ticking and my classical clock is ticking, and you compare them at one point in time. If they're synced up, then you wait, and if something happens to the clock that shifts its energy, therefore it's shifting its frequency, when you compare the two at a later time, you'll see that there was a phase shift between the clock's phase, the atomic clock's phase, and the classical clock's phase. So that's why we need to rotate these into the vertical position. Once the sensor operation happens, then we can rotate them back to the horizontal position and measure the spin. So basically, it's the exact thing I was describing earlier, where the height is equivalent to any angle on the Bloch sphere you can measure as long as you rotate your state into the correct position. So what's happening here now is when we have two sensors, the way that we generate our sensors now creates them with opposite directions on the Bloch sphere. So for example, the blue one is pointing away from us and the red one is pointing towards us. Now, if both atoms see this, if both positions in space, if they both see the same phase shift, they both rotate the same way around the clock sphere. Like, for example, they both go clockwise. And if they both go clockwise by the same amount, when you rotate back, one will be above the Bloch sphere, one will be above the equator, the other one will be below the equator, but then the sum of the two stays at 0. It's only when one of the clocks experiences a larger phase shift than the other that when you rotate both back, the sum is no longer at the equator. It's either above or below. And so that's exactly what we're measuring when we do these, all of the results I'm going to show you, is it's actually measuring the difference in the phases between the two states. And those phase shifts are caused by energy level changes that can be caused by energy level changes in the atomic system that causes the atoms to oscillate more quickly than the reference oscillator in the lab. So here's the data that shows the results of the experiment. So in the black points, I can't find my cursor here. In the black points, the phase insensitive points, that's what happens if we just run the sensor, but we never rotate the states into the vertical orientation. the mean angle that you measure doesn't change as you increase the magnetic field gradient. But if we put it into the phase-sensitive state, as we increase the gradient of the magnetic field between the two, the second-order Zeeman shifts between the two states caused by the magnetic field are going to differ from each other. And that's what this measured phase difference here is, these green points here. So this first demonstration is just to show that you can measure phase shifts, and the phase shifts we measure do have high precision. Are there any questions here before I go on to talk about a network with 4 clocks in it?
Are you going to show us if what's the regular result if we do not perform squeezing to a spin?
Yes, okay. I don't have that on my slides for the magnetic field gradient, but I do have that on the slides for the 4 clock sequence.
I see. Thank you.
Yes, so I'll go to the next slide in a second. So here we go.
Sorry.
Yeah.
Before you go on, can I ask a question?
Yes.
It looks to me in the entanglement 2 clock part, both the preparation and the measurement are important, right?
Mm-hmm.
And so how I just think it looks very hard. I mean, how do you adjust the measurement to the preparation? I mean, you can adjust the two system for the clock to adjust each other. I don't know how to ask. I'm just wondering how the measurement can achieve the two preparation to separated system very accurately.
I see.
Yeah,
Okay. So the short answer is you have to do it carefully. The long answer is all of these operations are performed with laser light, or I guess with microwaves. And so you need to make sure that the coherence of your light source is pure, and you need to make sure that the way it interacts with the atoms is also pure and has high fidelity. So for example, let's say we sent a laser pulse or a microwave pulse that changes the spin from down to up. If we continue that pulse, it changes it back from up to down again. And if we keep going down, up, down, etc. If you have a very bad pulse, you'll go from like all down to like 90% up to like 80% down to like 70% up, and it sort of washes out. So that's what we consider the fidelity, is how cleanly can you transfer atoms from one state to the other. So it's really just a matter of precisely controlling your laser pulses and your microwave pulses with high precision equipment.
So
I hope that answered your question.
So you mean basically you need high precision for the frequency transition measure?
Yes.
Okay, I see. Thank you.
Yeah, so those the devices I showed you in this laser system here, the drivers for the EOM and for the AOM, they have to be very low phase noise electronic signals, because any electronic jitter is going to imprint from the electronics onto the optics. And so that just and then the optics therefore imprint their phase noise onto the atoms. So every point in the experimental control has to be low noise.
Thank you.
Okay. I see we have 15 minutes left, and I think I have enough time to finish here. So before I just split the atom into 2 parts, but if you have a high enough fidelity transition, you could do this as many times as you want. In our purposes, we had enough fidelity to actually go to 4 clocks. So we just waited for them to separate, waited for the 2 to separate far enough before imparting an additional splitting pulse, so that you end up with 4. So now specifically what you're measuring is you're measuring not the average of all of them, but you're measuring phase of 1 minus the second phase plus the third phase minus the fourth phase. So really what you're looking at is sort of like a periodic change. If there was an oscillating magnetic field in space, you could use this to sort of like pick out the period of the oscillation of the magnetic field, for example. So now I can answer the question from a little bit earlier about how does this compare to the coherent state. So what this plot is showing is our sensitivity, our precision of the angle versus the number of clocks that you have. The black line is showing the quantum projection noise limit. The black squares are showing what happens when we use a coherent state in our system. We actually have noise higher than the projection noise due to other technical noise sources. Now, if you just had one clock and you squeeze that one clock, you get noise below the quantum projection noise limit. That's this blue point here. The problem is when you just have one clock, there's all sorts of other technical noise sources in your system. Like I was just explaining, any of that phase noise that you're using to drive the electronics are going to show up in the atoms. And that's what we're seeing here. If you don't operate in the phase sensitive, you just prepare the atoms and then never rotate them, the precision you get is all the way down here at the purple point. So we're showing that in our system, our experiment actually introduces all of this extra noise. So if you had 4 separate clocks, each prepared independently and each measured independently, if you were to do the independent measurements and then go over here and calculate theta bar, where you add, subtract, you only get an improvement that's as good as each individual measurement, and that's this blue dashed line here. So you can remain below the quantum projection noise, but you don't really gain anything in terms of other noises concerned. Now, if we instead use the entangled situation where we probe all of the atoms at the same time with the same measurement pulse, not only do we get reduced noise, because now we have 2 atoms, 2 atomic clocks that are seeing the same jitters in that electronic noise. So all of that noise is now common to both. So the difference between the two gets rid of that noise. That brings it down to the blue line. But then you get an additional improvement by having measured multiple clocks at the same time. So there's something called, I didn't mention it earlier, but there's something called the Heisenberg limit, which you probably have heard of in optics contexts, where the precision improves by 1 divided by the number of photons you have. So that's similar to what's going on here, is that now you can start getting improvement better than the quantum projection noise scaling, which is 1 over the square root of the number of clocks you have. Now you're going to get scaling better than 1 over the square root of m. So if our laser pulses were good enough, it would have been really exciting to see going to 8 or 16 clocks, how much this could have improved our measurement. But yeah, so this bottom green point here is our very happy data result, which is 11 dB or 11 decibels below the quantum projection noise and 4.5 below the best thing we could have ever gotten with 4 independently squeezed clocks that had no technical noise whatsoever.
I have a question.
Yeah.
About the sensor. When you split the sensor from 2 to 4, what is the squeezing parameter look like? The delta, delta C?
Delta C.
Yeah, the squeezing.
Oh, yes.
Yeah.
The squeezing parameter. So that's it's the variance of.
Yeah, the ratio between variance to the mean.
Yes, exactly. So it's the variance of this theta bar divided by 4 times the individual variance of a single coherent clock. Can I, maybe I can write on my screen here?
With entanglement or without?
Without it. So it's with entanglement divided by without entanglement. I draw. Aha, I can draw. Okay, so this is the one you're asking about, right?
Right.
Yeah, so it's this. where this is this thing here, divided by 4 times the variance of theta for the coherent state. That's the formula.
But here the theta is the what you can measure, right? And this is from the fluorescence signal, right?
No, sorry.
Yes.
I should have been specific there. This is all done with the Q&D measurements because it was done quick. It's done so quickly that we can do both with the Q&D measurements.
Okay, I see. Thank you.
I forgot to mention that. Thank you for asking. Okay, great.
I'm sorry, I missed one basic part. Why the noise of the coherent is larger than the separate one? I'm just don't.
Oh, so this is when we have no squeezing. This is when we have squeezing, but only for within one clock with one spatial position.
Okay.
Yeah, so here, so this is the Bloch sphere with this, and then here's the Bloch sphere with the squeezed.
Oh, okay, thank you.
Okay. So good, there's just enough time to tell you about the gravitational sensor. So there's a lot of stuff on this slide, but basically this is sort of the summary of everything that's going on. I've already shown you the first parts where you have the initial split, we split into 2, and then we produce the entanglement with the quantum non-demolition measurement. It's at this point right here, now we do something different, which is we release the atoms completely into free space and we let them fall for a long amount of time. Now, once you have each of these 2 spatial modes, now you can apply that Mach-Sender interferometer sequence, where the atoms split along different paths, and each path picks up a different phase because of gravity. So now we have 2 interferometers, one measuring gravity in this position, one measuring gravity in this position, and then the final collective measurement tells you the gravitational gradient between the 2 sensors. And again, these are just reiterating every step of the process as we go along. The very first slide I showed you was a simple pi-half beam splitter. Because we have a squeeze state and because we have to start with atoms in an even superposition of the 2 up and down, we have to do something a little bit more complicated. This sort of looks like an echo sequence where you have a pi-half pulse that with the microwaves, which don't transfer momentum, interleaved with a bunch of Raman pulses which give and take away momentum transfer between the 2. So by doing this specific sequence, we're able to split them and recombine them with, now we have twice the amount of momentum transfer that we had if we just had a normal Mach-Sender sequence. So we're getting the improvement from squeezing here, but then we're also getting an additional factor of 2 improvement because we have additional momentum transfer. So this is the contrast of the system if we just use a single one of these gravitational sensors. And this actually goes back to the question that was asked just a few minutes ago about how well do you have to make these states. So this represents the fidelity of our total sequence of pulses. So this is 40% contrast. If the laser pulses were absolutely perfect and there was no error, you would get 100%. For types of sensors like this, 40% is not an unreasonable contrast value. But for us, it was very difficult to get to the 40% in the first place. We had to do a lot of work getting our laser beams and our laser system as low noise as possible. So the grand finale of our data taking is this figure here. This is showing what happens if we operate the gravitational sensor with coherent states versus operating with the entangled states. And you can see that for a single, this is the phase uncertainty or the precision versus the amount of samples that you average over. So for a single shot, there's actually, it looks like there's only a modest improvement. There's like at most about 2 dB of improvement from coherent state to entangled state. But what's important in these types of measurements is how many times you have to average to get the precision you want. So if we wanted, for example, let's say this is 1, 2, 3, 4. This is like 5 milliradians of precision. With the entangled state, you can average for only half the time. So this can be very important if, for example, you want to measure with high precision some gravitational effect, but your sensor is sensitive enough to pick up the tidal forces from the moon. So if you needed to do a long measurement over many hours, that's going to affect that the tidal forces would change over that time. If you can do that in a shorter amount of time, then you're less sensitive to those changes. So the future of entangled atomic clocks, there are several theoretical proposals showing what could happen next. The most obvious thing that can happen next is if you had multiple cavities in multiple locations. However, they all shared the same QND pulse. So this is a little bit challenging because every time the laser light goes through a mirror, you get some losses. So the more of these cavities you put together, the more loss you're going to have at the end of the day, and the less improvement you get from adding an additional laser cavity. But if these types of systems can be sufficiently dealt with, then sort of a grand pie-in-the-sky goal is to have a synchronized satellite network that has photonic links between all of them that are synchronizing and entangling all of the different clocks. So this would just be a improved global positioning system, or you could use it as even a communication system. If you're able to entangle 2 different observers' clocks, if you create sort of if you're creating a entangled variable between the 2, you could potentially use that for, let's say, secured time sharing. Like your atomic clocks essentially would be somewhat protected from an eavesdropper, for example. I'm running out of time, so I want to just stop. This is basically the end of my talk, so I want to stop and see if anyone had more questions.
I have a simple question about the gravity gradient part. When you try to measure the gravity gradient, you mean the gradient in spatial difference, but the gravity, as everyone knows, is very small, so the gradient for short distance is quite small. So usually, what's the limit? Usually, how separated the entangled system should be to make a significant measurement you predict? Yeah,
I see. So our systems were only separated by like I think like half a millimeter, something around there. Yeah, definitely the more separated you get, the better gradient you're going to measure for sure. I mean, like I showed in the opening slides, the equivalence principle test that our lab did, that was over, many meters of distance. So yeah, I wouldn't expect you to be able, well, let me put it this way. Over this distance of just a millimeter, you're not measuring a very big number, but you're measuring it more precisely than you would if you had used a coherent clock. I don't know if that answered your question sufficiently.
So you mean it's a way to make more precise clock, or
Yes, exactly.
I see.
Let's say, well, here's a good example. Let's say, for example, that you brought a really big, heavy block of lead or something right next to your experiment, and then you took it away, and you measured this very tiny distance with the coherent clock. You probably would end up getting a null result. So your report would be, I didn't measure any difference. But maybe with the entangled clock, you'd have enough improved sensitivity to actually measure the difference between a mass that came in that was heavy enough to maybe detect it. And for these, there are experiments like this. They do use gravity gradients larger than a millimeter, but they are able to detect heavy masses being brought in and out of the lab.
Okay, quite interesting. Okay, thank you.
Is there any further questions? Okay, if there's no further question, let's thank the speaker again.
Thank you.
Thank you.
Thank you, Ben. Thank you. Sorry, I was a bit late of your talk. I was in another meetings, but I enjoy your talk very much.